Let me introduce our speaker today. I'm thrilled actually to have her with us. She is a geologist at Yellowstone National Park, specializing in the application of thermal infrared remote sensing and digital geologic mapping techniques. Everyone will have to say that quickly before you leave here today, or we'll keep you in. And she's studying, of course, applying that to Yellowstone's hydrothermal system. Before working for the National Park Service, she taught geology and physical geography and digital mapping at Laramie County Community College in Cheyenne. She holds a doctorate in quaternary geology and remote sensing from University of Wyoming, as well as a bachelor's degree in geology from Rutgers University. She told me to pronounce her name as Jaworowski, but I'm not going to do that. Please welcome Dr. Cheryl Jaworowski.
Dr. Preston, thank you very much for your introduction. Is my mic on?
Yes.
Okay. You're all hearing me in the back?
Yes.
Okay, that's good. What I want to introduce you today is a new way of looking at Yellowstone. And the picture behind me gets you thinking about a new view of the Yellowstone hydrothermal system. If there's nothing else you take home today other than that, it's immense, it's huge, and really special globally. That's all you really need to know. Anything else that you pick up from the talk, to me, is gravy. Okay, but hopefully that's the thing that you end with. And I want to first start getting you looking at this system from a different perspective. Many of you travel to the park via car, walk on the boardwalks, but I don't know how many of you have the opportunity to fly over the park. When you do, even if you've been here for a long time and have never done that, it really gives you a new appreciation for the vastness, the size of this hydrothermal system. So behind me is a view taken from a helicopter of the Upper Geyser Basin. Old Faithful is right here. You can see kind of the boardwalk area, the road system. This is Castle Geyser and Grand right here, and this is some of the boardwalk. This was an early morning flight in August of 2009 when it was very calm, and of course you could just see all the heat and steam from the thermal features, all the geysers in the Upper Geyser Basin. So that's what we're going to get you looking at, not only in visible imagery like we have here, but also in thermal infrared. So you're going to have to put on your thermal infrared glasses at some point during this presentation and start looking at this landscape, not just with what your eyes can see, but your thermal infrared sensing eyes could see. And also, one of the things I want you to do is think of Yellowstone in the context of the greater Yellowstone area and how it relates to hydrothermal features surrounding the park. So I don't know if you've ever thought about that, but essentially on this map here, okay, this is kind of the Montana area, Idaho, you can see the Wyoming boundary right there. All the red dots show you all the thermal features outside of the park. Now, Yellowstone is the little yellow polygon here, and I didn't put all the red dots for the 10,000 or more thermal features that are on this map. It would just be one red blob, so I just left it as a big yellow sort of square. But one of the things you can see in this context of the greater Yellowstone area or ecosystem is that there's extensive geothermal features all around the park. So again, starting to think about Yellowstone in a broader geographic perspective is important. You also notice, as some of you are probably well aware, that not only is it 3 states that are at the nexus of Yellowstone, but you have numerous, in the green, land management agencies. In the red, here and here, are known geothermal resource areas. And then what you also see on this map, in this color here, the state of Idaho basically mapped out its geothermal resources. In this color here, the state of Montana mapped out its geothermal resources. And in Wyoming, these three here, Bighorn Basin, Wind River Basin, Green River Basin, are the geothermal resources that the state of Wyoming mapped out. As usual, if you look at it in a little different perspective, which the Bureau of Land Management did, they kind of looked at it as a system, and you can see how it kind of crosses state boundaries, particularly as you go here from Wyoming into Montana. And it starts giving you the idea that this hydrothermal system really doesn't know the boundaries, whether it's land management agencies, the Yellowstone Park boundary, or the state boundaries. And as a geologist, that's a good perspective to look at it. Just like bison don't know park boundaries, well, the hydrothermal fluids don't know the park boundaries either. So, in Yellowstone, what are we trying to protect in thinking about this system? Like you, I love to take pictures of the individual thermal features. They're just beautiful, they're fascinating, and there's a great variety there. But we need to start thinking beyond the individual features. We need to start thinking of them as globally rare, which I hope I'll convince you if you don't already think that they are, and it's a composite natural resource. It's much more than the individual thermal features. You have to link the individual thermal features to the cold water that comes in both locally and from a distant source, and also the hot water discharge. That's all part of thinking of it as a composite resource and as a system. And it's a resource that I know many of you are aware supports recreation, economic benefits, and you may not be as much aware of the scientific and cultural benefits. Natural heritage, I'm sure most of you are aware of, because many of you, probably as a young child, as I have, were brought to the park to kind of see it and were enthralled. So what we're trying to do is to protect an extraordinary combination of natural processes that results in this really unique hydrothermal system. And let's give you a little perspective about how unique this system is. This information on number of geysers was taken from Barrick in a 2009 publication. And if you look at this graph here, it says there are about 940 geysers worldwide. And this yellow bar, representing Yellowstone here, about 500 of them are in Yellowstone. So just looking at those two numbers, it tells you that the Yellowstone system is large. And the number of geysers is just one way to kind of measure the size of this system. And you'll see that there are other places in the world that have some, like in Kamchatka, Chile, New Zealand, Iceland, and many others that make up the rest. So it does put Yellowstone in a really unique place globally, in that it has a very large concentration of geysers, and as most of you know, a lot of them are in the upper geyser basin in the Old Faithful area. So hopefully you're convinced right now, if you hadn't already been, that Yellowstone is truly unique in the world. So what do we know about this hydrothermal system? We do know it has a large concentration of features on the surface of the planet. There are greater than 10,000 and counting hot spring, geysers, steam vents, and mud pots. About 500 geysers, if you're taking Barrick's basically estimate. It is powered by the Yellowstone volcano, so the heat that's driving this system of hydrothermal features, meaning heat and water, is coming from the Yellowstone volcano. And the thermal areas, believe it or not, only comprise a very small percentage of the land area, less than 0.6%. And on this map, I hope I can convince you of that. So all these little red places are the thermal areas, and of course this is the entire park. So it's just these very small areas where you have a unique combination of heat, water, fractures, and the rocks that allow the waters to come to the surface. Those are the special places. Now this whole area is a hydrothermal system, but it's in those special places that we can see it at the surface. So what is a hydrothermal area? Let me just stop that. I knew I'd have to do that. This is Mammoth Hot Springs. earlier this year, and believe it or not, there I am, and one of my coworkers, and we were called out to investigate some new activity that was in Mammoth Hot Springs, which is the park headquarters in the northern part of the park. And you can probably see some of the buildings around here of the park headquarters. And the question comes up, you know, are we in a hydrothermal area? Well, there's a little vent there we were taking temperatures of, and we were looking at the water that was kind of flowing out to try to see a little bit about its chemistry, just some simple things. And for myself, I would say yes. But I don't know if you would have just gone up there, walked on the boardwalk or gone on the road and gone around the historic buildings, that you would have easily said yes the way I would, that it's a hydrothermal area. So why am I saying that? Well, a few years earlier, we had done an investigation in one of the buildings about some hydrothermal gases that were accumulating. And it was the duty of our safety officer to basically close down his safety shop until those gas levels could be mitigated to something that was good for human occupation. So hydrothermal gases are something you have in a hydrothermal area. And when you have buildings like you do in the park headquarters, they can tend to accumulate. So in the park headquarters in Mammoth, hydrothermal gases are very well known, and there's a lot of active mitigation systems. So that's one clue for people who are living there, that they know it's an active hydrothermal area. Even though you have your buildings, your roads, and lawns, and everything else, if you look at the geology under the ground, it's the same geology. And your hydrothermal system actually there is mostly hidden. Just like the earlier map that I showed you, it's mostly hidden. So, how would I define a hydrothermal area? And this is a pretty steep definition, so let's go through it. It's an area where you have continuous geology, and in Mammoth, in the slide that I just shown, you have your hot spring deposit rock basically under all those buildings and heading down toward the river, so that makes sense to me. And it usually, but not necessarily, includes one or more hydrothermal features. And to map it out, I would say the surface boundary of it is the maximum area of hydrothermally altered ground, thermal deposits, geothermal gas emissions, or the heated ground. So, if I haven't already said this, the hydrothermal area is much more than individual thermal features such as the hot springs, the geysers, the steam vents, or the mud pots. I know they capture our attention, but to think about the entire system, we have to start thinking about the landscape beyond just the individual features. And in order to do that, I'm going to show you this cartoon, and it is published in a book by Smith and Siegel. And if you've ever seen that, you've probably seen this diagram. So this is a little block diagram, the surface of the ground here that you're used to seeing, vertically down to where you can get heat. You'll notice that underneath what we see at the surface, there's a whole bunch of cracked rock. And you get water coming in from locally and far away, cold water, moving down through the rock. And as you know, when you go deeper in the earth, it gets heated up, comes up through an intricate series of fractures. The hot water does, and it discharges in the multitude of thermal features we see at the surface. So it's this entire system that I'm interested in thinking about, and how each of these little features connect to it and this hot water system or hydrothermal system. So a geyser, one of parts of this system where obviously it periodically discharges some intense heat, steam. The hot springs, where you have less of a constricted opening, and you can see here how this hot spring is actually not far from the nearby river. So thinking about the river system here superimposed on a hydrothermal system is something that I've been impressed with in the last few years as I've done my work. But I don't know how many of you, when you go to the park, you know, look at the river nearby and this, and think about that connection, you know, underground with this water system. Mud pots, one of my favorites, maybe yours too, and it's more of mud and steam and water in a double boiler system. And fumaroles or steam vents, where you basically have a lot of heat and water that are above the major water table. So although these are beautiful pictures, and I know you all love to go up there and take them, what I'm thinking about here is trying to relate them to a whole hydrothermal system. So the words that I've just said, start putting them in that context rather than just a pretty picture. Another feature that I don't know that you've thought about, heard about much, are hydrothermal explosions. And this is one that happened in Biscuit Basin, in the Upper Geyser Basin. And you can see not only is it heat and steam, chunks of rock, obsidian sand are being blown out. So you can think of it as a dirty geyser eruption. They're unpredictable, very interesting to see. I've only seen the pictures, so I've not been lucky enough to see one actually from the boardwalk. But you can see the material being ejected, coming back down, and a little bit of a wash coming out here. Now, like you, we can look at these and try to monitor them from the boardwalk, since this is the most common geologic hazard actually in the park. It happens somewhere in the park every year, whether it's someplace visible, like in the Biscuit Basin area, or someplace in the backcountry. But in terms of monitoring, there are some things we can do from the ground, and there are some things we really need to get a little bit more of a perspective on. So using helicopters that are already on standby, we can do some quick condition assessments, get a little different view of it. So the pool that we just looked at was this one here. That was erupting. And it's a way just to visually see, that's a little hard to from the boardwalk, has this area changed since the last time we looked at it? Maybe if it was a little more oval, okay, we would have thought it was growing a little more or changing a bit. And this also impressed me when I went up. This was in March of 2010. Myself and the other park geologist who's in the audience, Hank Hessler, were up in the aircraft taking images, mainly to look at any cracks in the ground that might have been related to an earthquake swarm. But as we were flying over the lower geyser basin, midway geyser basin, and then finally to the upper geyser basin here, what impressed us most was the fact that here's the snow, and in this area, in March, you have no snow. That tells you, it's a good visual clue, that there's a lot of heat coming up there. You can see the steam here, but I don't know how many of you would have thought, well, this is all heated ground. Okay, and it's a good clue that it was. And from an aircraft, I was very impressed with how extensive the heat is coming up from this system beyond it. Even though I'd looked at these pictures before, even though I've looked at it in terms of heat, it's extensive. Here's another view of it from last fall where we had our condition assessment. And you can see this little pool here is a little different. So let me go back and have you look at that. Okay, so March 2010, fall of last year. Yes, there are different seasons, so you don't have the snow on the ground there. Different temperatures at the time that we were taking the picture. This pool to me, you know, just visually right now looks about the same size, but I was intrigued by the changes that were going on here. So we know there have been some changes, and that's one of the reasons we do these quick condition assessments, because the park is a rather large area, and two geologists can't really monitor everything easily, so we depend on lots of other people and some of these condition assessments. So the helicopter reconnaissance allows us to quickly focusing on areas where there might be some interesting changes that are reported to us. They're usually daytime aeroblique photographs. So one of us is on the other side of the helicopter taking visible pictures. The other person is taking the thermal pictures that you'll see here in a minute. And they're from about 500 feet above ground level. And what it shows us very quickly, very easily, is moderate to high temperature components of a hydrothermal system. Since it's daytime, we're not getting the lower end, we're only getting the moderate to high temperature end. So let's get you start thinking about the perspectives from this helicopter in the visible before I start showing you the thermal. Okay, so the Mammoth hydrothermal system. from the helicopter. This is the area you're probably most familiar with. This is one of my favorite areas on the Mammoth Terraces, kind of the canary area where there's always a lot of water, colorful microbes, and hydrothermal activity. And then you might have gone around the Terrace Drive here and looked at the active thermal features there. But as a geologist, when I think of that definition of a hydrothermal area with continuous geology, the continuous geology extends from here all the way through this, through the town of Mammoth, and down to the river. To me, that's all a hydrothermal area. Now, the vents where you see the thermal activity are just active in certain places, depending on when you visit there and the time of year. But all of that is the hydrothermal system. So I'm going from top to bottom and looking at it as a hydrothermal system. Okay, let's look at Norris. Okay, and this was from March 2010, that same kind of earthquake swarm flight where we were kind of looking at things. But we also captured this on the way from Mammoth toward our objective. And to me, what was fascinating about the Norris area here is look at the lack of snow, still in March. Okay, it's hydrothermal, very active heat. Okay, a couple of snow patches, but not a lot. The other thing that I was impressed with from this aerial view is this fracture system. Really easy to see from the helicopter. Not so easy when you're on the ground seeing these fracture systems. So just getting a little bit of elevation, a little bit of perspective helps you see about the fractures that help move the heat and water through this area. Lower Geyser Basin. Okay, let's see. Here's the road. You can see some snowmobiles right there. You've probably walked this boardwalk and looked at some of the springs here and here. But probably when you were there, you didn't get to see how much heat was coming all around here in these snow-free areas. That tells you something about the heat. Where there's snow, there's less heat coming up. And that's why the idea that these thermal systems are much more than the individual features, I think these pictures point out very clearly from the helicopter, and particularly in March of 2010. That was my first realization. Even having worked for the park still a few years before that, these pictures just said it all. Midway Geyser Basin. I'm sure you've seen Grand Prismatic from the air before. I know it was on the poster, just advertising the talk, but just look at all the heat, especially in places where you probably don't see big springs. Okay, this tells me that the heat is much more, the thermal system is much more than just the one single feature or a few features. Okay, little different time of year, but this relates to some work and some activity that's going on right now. Upper Geyser Basin, you probably always think of the Old Faithful area and that unusual collection of geysers. Maybe some of you have walked to the Lone Star area, and that's what we're looking at right here. This is the Lone Star hydrothermal system taken on a fall 2011 condition assessment flight. And when I took this picture, what I was impressed with was the system here, the fire hall, the river, and then all these other little parts of the system that you walk by on the trail and probably don't even realize you're walking by them. So I start thinking, how is this system connected with the river? How are they interacting? To clue you in, that's Lone Star itself. So if you've been there, you've probably been sitting right here. I think that's where some people sit, wait for the eruption of Lone Star Geyser. And you can see that when we took this picture, there were actually some discharge, thermal discharge from the feature that was going kind of like a spider's web from the geyser cone. But now, since you've seen enough of these pictures, these visible pictures, and started to think about it as much more than an individual feature, I want you to think in your mind, what would this look like if you put on your thermal infrared glasses, your heat sensing glasses, if you could see this like a bat or a snake would see it? Okay, now look at the temperature and heat. Okay, your feature, your geyser cone is right here. Look at everything on the hillside. Look at it going up around here. It's extensive. So this drives home the point to me that it is much more than just an individual feature. It's a system that we have to think about. We don't only do these for just simple condition assessments. One of the reasons we do them, it is a quick survey. It's relatively easy to cover the entire park. And it does allow us, like I just did earlier this week, to go out with other people and start discussing, using this imagery and information from the ground, how do you change your trail system? So you're providing good access through these systems where everyone can see it, yet also protect the system. So it's quite a balance. And so these images are used also for that, besides grounds information. And in addition, what we're starting to do is calculate heat from these images to be able to quantify the changes. So this imagery has multiple uses, more than just monitoring and protecting the system, although we are required in Yellowstone to do that monitoring of the hydrothermal system for its protection. Okay, now that you've sort of got an idea from the Lone Star hydrothermal system what a visible looks like and what a thermal, I'm going to ask you to do the same thing here. All right, so you can see this is the Old Faithful overpass. Many of you may have driven there. And you can see snow-free areas. So this should be giving you some clue. Now let's see what happens when we look at it in daytime thermal. Okay, the bright areas are where you're getting a higher temperature. So you can see here on the temperature scale, this is about 100 degrees Fahrenheit, and the bluer color is about 20 degrees Fahrenheit. And if we look at this, basically here we know this is heated up from the sun. Since it is daytime, you're going to have some solar heating. But right here, by the overpass, where they always put the wood chips, that's coming up from the ground. So in a daytime, that's what I meant about we have to look at the moderate and high temperature components of a system, because we do have the effects of the sun. Let's do another one right around Old Faithful. So this is the inn here. Old Faithful geyser is right here. I'm sure if you've been watching, waiting for the eruption, you've been on the benches right there. So put on your thermal infrared glasses and let's see what we'll see here. Okay, this is the daytime. Again, this is Old Faithful. And you've got this warm spot that most of you have probably walked by if you've been there. So, all right, you've seen the eruption of Old Faithful. You're coming around the boardwalk. You're going to go to Geyser Hill. And you see this kind of brown spot before you head off to Geyser Hill. Look at the amount of heat and the temperatures put out by there. Now, maybe you didn't notice it, but the bison sure did, because after a long, hard winter, that's where you usually see them sitting. So they're pretty good thermal sensors, maybe better than we are. And then one thing you'll probably also notice is in the obsidian sand around here, you'll see a warm area. That's some buried infrastructure in the Old Faithful area that we can see using these thermal techniques. All right, now I'm going to ask you to remember a few little things. The next images are taken from some scientific publications, and so they tend to have temperatures in degrees Celsius rather than the Fahrenheit. And I've broken them out, color-coded them to a low part of the system, because if we're looking at night with a fixed-wing aircraft, we can get down to the lower end of the system that we couldn't in the daytime. So the low end of the system is going to say 10 degrees Celsius, and that's roughly about 50 degrees Fahrenheit. The intermediate part of the system, which are going to be kind of warm colors, maybe yellows, oranges, are in the 15 to 40, and you've got 50 to 104 degrees. Not quite your bath temperature, a little hotter on that end, but maybe the high end of a warm spring. And the high temperature component of the system, 40 to 80 degrees Celsius, is going to be 104 to 178. You're starting to get up into scalding temperatures. So I've kind of broken out the system in the nighttime thermal maps that I'm going to show you of these areas, so we can start looking at how these parts of the systems are going to change over time. So here's one of the Old Faithful area. I've draped it on. The gray is some very detailed topography. You can see all the trees. Here's the Firehole River. This is Geyser Hill. You can see sort of a random pattern of reds, yellows, greens. Okay, and again, high part of the system, scalding. Intermediate part of the system, okay, a warm end for your bathtub, and the low part of the system that'd probably be a little too cool for you. So it's easy to see Old Faithful here, that warm spot, okay, but this you're looking straight down, not the air oblique, and other components of the system. What you also see is the infrastructure that's in the area for the 3 million plus visitors that come and visit Yellowstone, and of course most of them do come here. Another portion in the Upper Geyser Basin, maybe you've taken the trail, the old road here, or bicycled, looked at some of the features like Splendid Grotto or Riverside Geyser or Gone by Morning Glory Pool. Here we can start seeing what it looks like when we start breaking out the system in terms of high temperature components, intermediate temperature components, and the low components of the system. And once again, I've draped it on some very detailed topography that was just acquired in 2008. Another area, Biscuit Basin is just off there. Here's the main road, Firehole River, and I put some arrows here showing how ice from the last ice age had carved the hillside, which was one of my interests. But you can also see the individual features and how some of the individual features actually then start warming up the Firehole River. Anyone who has fished in the Firehole River knows that, you know, the Firehole River system is superimposed on the hydrothermal system, and then they're an integral part. Okay, so for that hydrothermal explosion feature that I showed you, we can monitor its changes over time, and the best way as scientists to monitor it is to look from one year to the next using the same conditions, same instruments, and see what happens. I was very impressed that in 2008 we could see that the lower temperature component of the system was more extensive than in 2009. And we've gone back with our collaborators who are working on this and saying, okay, is it good data? Have we missed something? We think this is real, okay, that in 2008 we saw more of the low-end component of the system using the techniques. Now, you might be asking yourself, okay, you're using helicopters, you're using aircraft, is there any way you can get a park-wide picture? And we have collaborated with other scientists who have used satellite sensors, and this gives you an idea. Okay, this is a Google map base, Yellowstone Lake, and all these little squares are what can be looked at from a simple satellite and estimating basically heat. So it was this year that this paper was published, so just in 2012, we've got a good park-wide estimate of heat using satellites. This is the best estimate so far that I know of, and it's roughly about 2 gigawatts total from all of these areas. Now, these satellites had a big area to look at. It was a 1 kilometer footprint, whereas the other maps that I was showing you were 1 meter or less, so 3 feet or less. So you can see different details in the system. You can get different numbers depending on whether you're using satellites or whether you're using something close to the ground or from a helicopter or aircraft. So this does give us a synoptic view of the system from the satellites, and it was a good study that showed the limitations and the possibilities for just easy monitoring from space. So what's really new from what I've been saying here? Well, since 2007, which is when a lot of this thermal effort began, we've documented some of the natural and temporal changes of heat for just a few thermal areas, not park-wide at 1 meter. And what you're going to see here as I go through this summary is a simple technique where you can walk the boardwalks, have a paper map, and use pencils and get your changes. Because we always get the questions, especially in Mammoth, aren't the terraces drying up? So I wanted something simple where we could answer that question. So watch these maps as I go through the summary and you'll see the changes. This map from 1969 image, where the water was, to a little more current, 2009. We have an idea about how these systems vary over time and some of the human impacts. We also have an idea that the hydrothermal system is much larger than the individual features. So if you want, I'll go back through this again. We'll just watch the changes on the map. Okay, that gives you an idea of how the water just changes from year to year. And with that, I'm going to end the talk and open it up for questions about anything that I've just discussed here. Thank you. Yes?
What about vegetation? Are there any specific plants that indicate a thermal area?
In the low temperature part of the system, you see a very intricate relationship between some plants and the low end of the system. Just last week I was out with some of the park botanists where we were looking at that with regard to trail placement, because usually where the trail goes you're looking at the low end of the system and you're trying to place, okay, let's not stop on this rear plant and let's not get to that thermal feature, so you tend to use that information actually all together. Okay.
I saw in your chart at the beginning it said 1,200 geysers and then it's down to 900. Is that because of Iceland? Iceland using geothermal activity to heat their homes and stuff? Or
that is correct. The numbers do decrease when you develop an area, because if you're looking at geothermal heat, you're talking about heat and water that you're extracting, okay, for human use. And a hydrothermal system, hydrothermal means heat and water, so it's kind of one or the other. So that's why you do see declines in the numbers from Barrick's study.
And was the areas mapped in Idaho, is their intent to utilize or hydrothermal activity for energy use, or?
Correct. I think probably if you just go to the Idaho Geological Survey, you probably can find, like their website, you can probably find some of their uses. They do use geothermal, and I know in the last few years there's been some active geothermal drilling projects in the Snake River Plain to see how they can use it, particularly I think for some of the military bases there. And what I'm also going to ask at this point, if there's more questions about geothermal, I want to introduce my co-author, Hank Hessler, who is also a park geologist and a geothermal specialist. So do you want to add anything to?
Fine.
Okay. I got an okay on that one. Okay, right up here.
My question is that we're in a 20-year drought now in the West, and I don't see that ending anytime soon. How do you expect this long drought to affect this entire geothermal area, even the larger one you're talking about?
It's a great question, and we had actually a great experiment that started last year and is ongoing right now. As some of you know who live in the area, last year we had 200% normal snowpack. Okay, that was a lot of water that got put into the system. So as we're monitoring now with these techniques, we can see the natural experiment as it's going from very high water year to our current water year and others. And as we monitor this system, we'll better be able to answer that question. But the answer is right now we don't know. And we tend to say that a lot as scientists, that we really don't have the good science yet to definitively answer something. But I do think from what I've shown here that we have some good techniques to monitor and get that answer. Okay, and then behind you there was a question.
So just following up on geothermal for heat and power, is it consumable? Does it get used up, or is it renewable? Can you
Okay.
overuse it and then wear it out?
I do want to divert that question to our geothermal expert. You want to come up here, Hank, introduce yourself and use...
I don't want to.
By the way, some of you remember Hank. It was, what, 4 years ago? Was it? Boy,
Oh,
a few years ago, Hank was one of our speakers here. So good to see you.
It's a good question. It is technically considered renewable because if you basically you take out the water and the heat, you extract the heat, you put the cooler water back down, it can then extract the heat again. So it is technically considered a renewable resource. The problems why it affects geysers is geysers also need the heat end of it. So if you're in New Zealand primarily, they've lost a lot of their geysers due to geothermal development. And I come from a geothermal development background. And we've done studies in Cody. We think it would be great to use in Cody. So we're not against geothermal development. However, we do believe that the world's greatest concentration of geothermal features this unique concentration does deserve protection. Because after all, the reason why the park was created in the first place were the geothermal features. Now there's a lot of other very positive reasons. So yes, geothermal is renewable, but you still impact the heat balance and the water balance, and will impact any nearby thermal features. Is that?
Yeah.
Okay.
Okay.
Is there much geothermal activity on the Mirror Plateau?
Trying to think. We haven't done any imaging there. There should be. I know nearby, Hot Spring Basin is an area that we've monitored kind of in the backcountry ever since we kind of started this. And it's rather significant, but we haven't specifically focused on the Mirror Plateau. And I haven't looked at any images there, so as a scientist I'm going to say there should be, but I can't think of the pictures in my mind that would demonstrate that. Would you like to add anything? Okay.
Have time for maybe one more question? Anyone?
Okay, right here.
The Thermopolis hot springs part of this system?
Okay, I know Hank studied that, so he's really going to answer that question.
She's a plant.
Simple answer, no. Thermopolis and most of the hot springs in the state, and Wyoming has a great series of hot springs, is due to the plumbing system. In other words, the cold water comes down from the mountains, goes deep in the basin, and just heats up due to the normal temperature increase with depth. And then at Thermopolis, there's a very interesting fault system that allows that water to get to the surface before it cools. Now, the sign there that we've been trying to correct for over 20 years says it's due to volcanic processes, but it's not. There's a series of great reports that have been published by a variety of people that show it's just a nice Wyoming basin sort of water comes down, heats up, and then gets to the surface quickly before it loses its heat.
Great. Well, it's a great pleasure to have not only Cheryl, but Hank also here today. It's good to see you again, Hank. I'm glad you guys were able to come in. And thank you so much for joining us today. And Cheryl, wonderful job.